Okay, so we're going to do limits at infinity today. So I need you to try to graph this on your own first. Rational functions, use the concept of vertical asymptotes, horizontal asymptotes. Don't forget all that stuff, right? So f of x equals 3 over x minus 2 has a vertical asymptote at 2. And it has a horizontal asymptote at 0. Very good. And then you can come up with a couple points yourself to plot on this graph, but I'm just going to write, this is a rough sketch, this is not exact, but you're going to get something like this. Agreed?
Agreed.
Alright, look at part A. It says, what is the limit as x is approaching 2? And I know it's hard to see, but there's like a little negative sign up top. Did we talk about what that meant last time?
Yes.
So that means you're approaching from the left. So if you're approaching from the left, what's happening? It's going towards negative infinity. But if you're approaching 2 from the right, it is going to positive infinity. So then I'm going to add something. So then what is the limit as x approaches 2 of 3 over x minus 2? Does not exist. Very good. Because from the right side, you are going towards positive. From the left side, you're going towards the negative. Different directions is not matching. The limit does not exist. Cool? For this type of limits, okay, when you have asymptotes, vertical asymptotes, and you're going to be able to tell because you should know that if you have something like a rational function, there are going to be vertical asymptotes present. Correct? When that happens, more than likely you are going to get infinity or negative infinity. There's two methods of doing this that I suggest. One is you can come up with a rough sketch yourself because you will not have a calculator for this test at all. Or you can create a table on your own. Okay? So honestly, if you're more of a visual learner, it doesn't take you that long to come up with a rough sketch. It doesn't have to be exact. The only things that need to be exact is obviously your asymptotes, correct? So, if for example, you look at number 2, you have an asymptote at 4. And on number 3, you have an asymptote at 2. And on the last one, you have an asymptote at think about it. Negative 2? You do not have an asymptote. We'll talk about that one in just a second. Okay. This 2. Do you agree? Alright, so let's say we come up with a sketch. And you have an asymptote at 4. And where else do you have a... Now you have a horizontal asymptote at 0. Remember, because the denominator, the power in the denominator is higher. So now if you just plug one point, pick one value. Pick an easy value, 0. If you put in 0, that would be 3 divided by negative 4, which means that you're going to be in the negative side, right? Which means that your graph is going to be down here, correct? Which means that your graph is going to be up here, right?
Yep.
You got your sketch, you should be able to answer this. Okay, what happens is x approaches from the positive side.
It's going to go up infinity.
And from the negative side?
Negative infinity.
Do you guys see how easy this could be if you come up with a sketch? Alright, try number 3. And I want you to try number 4. Take your time on number 4, okay? So pause the video and come back when you are ready to check your answers. Alright, check your answers on this one. Alright, for number 3, we had said that we had a vertical asymptote at 2. And I plugged in some values, and I found out that the graph looks roughly like this. So as you're approaching from the right-hand side, you're going towards negative infinity. And as you're approaching from the left-hand side, you're going towards positive infinity. Correct? Now, number 3, what's the difference between, the last one and the other 2? Yes?
Question about number 3.
Uh-huh.
What side those two things are going to be on? Do you have to plug in points? Is there another way to figure it out?
Plug some points in to make sure.
But since the numerator is always negative, you can always say that.
That's on number 4, okay? So, number 4, what I did is I actually, once I figure out my asymptotes, I did not assume that it's alternating, okay? Don't assume that. It doesn't always happen that way. It doesn't take you that long to check a couple points. But, if you just think for a moment, because your numerator is negative, no matter what you plug in there, it's going to turn negative, which means you're always going to be below. Again, if you don't trust yourself, you could have plugged the number that's before -2 and one that's after -2. You would have then gotten negative numbers, which means that your graph would be located below that horizontal asymptote, which means that your limit as x approaches -2 will actually exist, and it would be -infinity. Easy?
Yeah.
Okay, now here's my question to you though. How are you going to know that this is going to happen? Because we've done limits with rational expressions, but we haven't been doing this. So on your test, I'm not going to tell you what's going to happen. All the types of limits are going to be on the test, and it's going to be your job to recognize what to happen. Okay? So here's what I would say. If you were to plug in 2 here, you know that that's not possible. Is there anything algebraically you can do to make that go away? At that moment, when algebraically you can't do anything, that should be your hint. Okay, maybe I should sketch this out. But if you're able to do something algebraically, try that first. The way limits work, there's an order in which you need to do things. First, plug in the value. If it works, you're good to go, right? There's no point of trying to do anything else. If you plug it in and it doesn't work. Number 2, remember all those algebraic techniques I showed you last time. You need to try them. If you try them and it works when you substitute in, then you're done. But if you try those techniques and it doesn't work, more than likely it's going to be something like this. Okay? Alright, so let's keep going. The whole vertical asymptote, that was just me reminding you how to find vertical asymptotes, and we're running out of time, so let's move on. Okay? So now that you have some kind of practice with this, can you try to solve this on your own? It's 8 through 13. Keep in mind, not all of this means that they're infinite. Use all the techniques that I've shown you so far. First substitute. If it works, then you're done. If it doesn't, then you have to use other techniques. Number 8 is obvious that it's not going to work and there's nothing you can do. Agreed? So you would straight go to what we've been doing today. But if you get something more complicated like 11 through 13, I would first look to see if I can do anything before I assume that it's going to go towards infinity. Cool? So try those out. I'll work them out. I'll show you the answers here in just a second. Yes. Alright, so check your answers for number 9. Here's the graph. And if you're approaching 1 from the positive side, you're going towards positive infinity. Yes. For number 10, you will notice that it's the same graph as number 9, but that negative flips it over the x-axis, which means that then this time you're approaching negative infinity. 11 and 12. Remember that when your numerator is bigger than the denominator, you can divide it to find its slant asymptote. So I did synthetic division to find out that my slant asymptote is located at y equals x minus 2, which there it is roughly. Here's my vertical asymptote. I plugged in one value to the left and one value to the right of the vertical asymptote, and I found out that the graph roughly looks like this. As I'm approaching from the left side, I am going towards positive infinity. As I approach it from the right side, I am approaching negative infinity. And last one, again, plug in your value first. You get 3 in the denominator and you get 0. 0 divided by 3 is 0. Questions? Concerns? Are we good? Last topic, limits at infinity. So this time I'm going to ask you, what is the limit as you approach infinity? Okay, not always. So sketch this graph for me and then use the graph to answer part A and part B. Alright, these are the rules you're going to use to find limits that goes towards infinity or negative infinity. By the way, they're the same rules that you use to find horizontal asymptotes. So, what? If the degree of the numerator is less than the degree of the denominator, you will have your limit would be 0. Okay? Oh my God. Number 2, if the degree of the numerator is equal to the degree of the denominator, then what happens? It's the ratio of leading coefficients. Seriously? Oh my god. Alright, so it's going to be the ratio of those two. Okay? And just like with asymptotes, you guys remember that when the numerator was greater than the denominator, then you had a slant asymptote. So unfortunately for you, what's going to happen here is that you're going to have to try to do something else, which is other processes that we tried. So if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function is either going to be positive or negative infinity. Okay? It's going to be one of those. And you're going to have to... Well, I guess so, yeah. You technically have a 50-50 chance, but you're going to use some of the techniques I'm going to show you to solve this. Okay? Alright. So I'm going to practice... I'm just going to do one with you, and then I'm going to let you practice the rest. Okay, so look at number 15. You have the limit as x approaches infinity of 5 minus 2 over x squared. Now, my suggestion is, do you guys remember last lesson I gave you some properties of limits? Remember that I told you that the sum or difference, you could actually break this up into limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Agreed? Now, one of the properties tells you that I don't care what the limit is approaching of a constant, what is the answer? The constant, so this is 5, correct? Minus. Look at this one. Isn't the denominator the degree bigger than the numerator? So that means that your limit is? Which means that the limit of this entire thing is? 5. The degree is 2. The degree on top will be 0. So the limit has to be 0. Okay? I want you to try all of the ones where you can apply the rules. Leave the ones where you have the numerator greater than the denominator blank. We're going to go over those together. Okay? So try. So basically you're leaving blank number 19, 20, and 21. Alright, so you're going to tell me, on number 16, what rule did you use? The degrees are the same, so the limit is 2. Number 17. 0. Number 18. 2/3. 19, 20, 21, let's skip it for a moment and go to 22 real quick. Let me ask you something. You know that the graph of sine is oscillating, correct? So typically at 0, you're up here, right? And then you just kind of bounce up and down, and you continue to go, right? Up and down, right? Well, let me ask you, if you continue to go on forever, are you ever really reaching anything? It is going between -1 and 1, but that's not specific enough. It needs to be you're following a value. So I understand that it's going between -1 and 1. Do you guys agree? But that's not a specific value. It's not. You can't just say it's 0. You can't just say 1.1 or 0.5 or -0.5. It's oscillating. Remember, when something is oscillating, it does not exist. Cool? 23. It's just going to require you to use, honestly, just your parent function and honestly, yeah, your common sense. You know that this cubic function looks like this. What happens as you're going towards infinity? As you're going to infinity. Oh, I'm sorry, I didn't see that. As is going towards negative infinity, I'm sorry. So that means your x's are going that way, which means your y's are going that way, which means it's negative infinity. Thank you. Very good. So yeah, pay attention. Make sure you look at the sign. Yes, I'm sorry. All right. Number 19 through 21. There is 2 ways that you can do this. You ready? So I'm going to kind of go fast over this because we have 10 minutes left. I am going to show you how you can actually just reason yourself through this and get an answer, and then I'm going to show you how to do this algebraically. Okay? It depends on you. Okay? Let's talk about it. Look at number 19. I know I told you that you can't really plug in infinity. I agree that if you plug in numbers that are larger and larger, then this will continue to get larger, and so will this. Once it's large enough, would that... So we can really ignore that part there. Okay? Agreed? Now, you look at the leading coefficients. Aren't they both positive? So wouldn't it be a very large positive number divided by a still large number, but not large infinity? Correct? I guess. But now, here's what I'm going to do. Just with this problem, and for time's sake, I'm going to algebraically, and then you can solve the last two on your own, whatever method you want. You ready? So algebraically, this is what the limit is x, the denominator being greater than the numerator as far as the power goes. So that way I can use these rules of limits. Okay, so you ready? Remember that with any expression, as long as you do one thing to one of the parts, the 3x squared, looking at the denominator. What I want you to do is ignore the 3, and I want you to divide every single term by x, and we're going to simplify things. So this becomes limit as x approaches infinity. 2x to the third divided by x squared becomes 2x plus 5 over x squared. Agreed? That's not going to limit as x approaches infinity of 2x plus 5 over x squared over limit using the properties. And then if you wanted to, but I'm running out of space, you can say, what's the limit of this? Approaches infinity of this. Well, now do you see how your denominator is bigger than your numerator? It's 0. Using the rule, right? The rule says that if the degree on the denominator is bigger than the numerator, it is 0. Correct? Okay, so I guess I do have to show that step. This, I'm going to totally come over here. This thing becomes the limit as x approaches infinity, 3 plus the limit as x approaches infinity of 1 over x squared. Remember, you can literally break them. So now, using the rules is 0. And then, when well, let's think about it. If you have infinity, when it gets so large, would it matter that you divide them by 3? Doesn't that work? Okay? 21 on your... Put it in there, but I think it's page 877, I think. Hold on. No. 7... Hold on. Numbers 1 through 32. 1 through 32.
Wouldn't that not really work for 20?